Welcome to Chapter 3. We're going to start talking about two-dimensional kinematics. Two dimensions means that we're dealing with this in both x and y. And if you will, if our paper here, if the screen were a view out a window and we were watching some kid kick a ball, right? We'd be looking for how do we describe the motion of that ball? All right, that's what we mean by 2D kinematics. So there are several tools we're going to need in our tool chest before we can actually do this. You should know, well, without a doubt, you know the Pythagorean theorem, right? That if we have a right triangle, then the side a squared plus b squared equals c squared. So we can sort out the lengths of the sides of a triangle. Well, we're going to be doing this over and over again, except we're going to call this the x length, and we're going to call this the y length. And we're going to be using our vector notations I and j. And we're going to be asking, okay, if I walk 3 miles east and then 4 miles north, right? Then how far away from where I started am I? Well, of course, the answer is 5 miles, right? 5 miles. Or if I do 3 kilometers, 4 kilometers, then I'm 5 kilometers away from where I started. Right? We just use the Pythagorean theorem to figure out what is the distance from my starting point to my stopping point. So another big part of using the Pythagorean theorem or doing 2D kinematics is that motion in the two directions is essentially independent. Right? They are orthogonal directions. That means they are independent of each other. So if I was standing in front of a classroom and I was walking back and forth and back and forth in front of the board, that would never change my distance towards the back of the room. I'm always going to be at the front of the room walking back and forth and back and forth. It doesn't matter how much I walk back and forth. I'm always going to be at the front of the room. Why? Because my motion back and forth in front of the board has nothing to do with my distance from the back of the room or where I am in the other direction in the room. That is an independent coordinate from my back and forth. So we've been talking about independent coordinate systems. X and Y are going to be independent from each other. I hat and j hat independent from each other. We've often used graphical methods, and I know back when I was a Cub Scout we did this all the time with maps, and we use graphical methods to say, okay, how far am I going if I go from this point to this point, and I just, all right, I'm going to start here, I'm going to go to there, I'm going to go to there, I'm going to go to there. I'm just going to use a ruler to say, okay, I went this direction, I went that direction so far, and that direction so far. All right, how far away am I? All right, so graphical methods are they're decent if you're drawing on a piece of paper, kind of thing that used to be fun when I was little, just playing around. But there are analytical methods for doing the same thing. So we're going to start talking about vector addition and vector subtraction. So we're getting a little bit more formal on how we do this. Right? A vector is just a quantity that has both a size and a direction. Right? And we write them in a couple of different ways. Some books, I prefer putting the little arrow over the top, like I've done here with A with the arrow over the top and B with the arrow over the top. I prefer the little arrow because it makes it clear to me that that's a vector since it's got something on top of it pointing, and I want a quantity that points in a direction. Some books, they will make vectors bold, and they'll give them a bold font to indicate that it's a vector. In my notes, I'm always going to be using a little arrow on top just because that's my preference. So just like in regular algebra, if you have a vector A plus a vector B, well, that is also the same as the vector B plus the vector A, right? I mean, it doesn't really matter if I walk 5 miles east and then 3 miles north, or 3 miles north and then 5 miles east. I end up at the same place, right? So that's all well and good. The other thing is, if I take A and subtract A, I get 0. Great. Math with vectors works kind of like you expect it to, right? And vectors are written as a sum of their orthogonal components. Remember, these pieces are independent of each other, right? So I know how many steps to take in I hat. I know how many steps to take in J hat direction. I know how many steps to take in the K hat direction if I could walk in all three dimensions. So if we look at analytical methods, right, here's the important thing. These are independent coordinates, right? So I can only add up the i's and I can only add up the j's. I never get rid of that, right? And so if I'm adding a plus b, it's the x component of a and the x component of b add together. And then the y components add together. Or if I'm subtracting, it's ax minus bx and ay minus by. But at the end, I've still got a vector. I still have these unit vectors right here. Nothing's disappearing there. So it's sort of like if we were talking about fruit and we said we let I hat be oranges and j hat be apples, right? I can't add oranges and apples and say, well, I've got this many apples. No, I can't. I can't add oranges and apples and say, well, I've got this many oranges, right? So we have to keep in mind when we're dealing with vectors, when we're adding them and we're subtracting them, that we're always going to have a vector in the end. That part of it's not going to go away. Now, if you look at this one, right? One way to look at this one would be to say, oh, wait. Okay, so this is my only I component, right? That's my only I, and here are my J components, and there's my K component. All right, so I ends up right there, and it's got the I hat there. That doesn't disappear. And then there's this part of it with the J hat right there, and then there's the K hat. So the vector part of it stays with us. We never go from adding two vectors to end up with a scalar. I see this all the time in problems. Kids will add 5a plus 10j, and they'll call it 15. Well, that makes no sense to me, right? Because going 5 east and 10 north adds up to going just 15 where? Right? 5 miles east, 10 miles north, and you can't get to just 15. You still have in there, I went 5 east, 10 north, right? Now I can ask you for your total displacement, how far away for you from where you started, right? And we can do that. We can go 5 east, 10 north, and say, well, I'm the square root of 5 squared plus 10 squared. Right? And I can't quite do the square root of 125 in my head, but that's where we would be. Square root of 125 miles or kilometers or whatever our units were, miles or kilometers away from where we started. All right? So we can talk about the magnitude of the vector. All right? And when we talk about the magnitude, this is what we're talking about. The magnitude of the vector. It is the exact same symbol we use for the absolute value of a number. All right? Because when we're getting the absolute value of a number, we're just asking what is the displacement from the origin, and we're not worried about direction anymore. While when we're looking for the magnitude of a vector, we're looking for the total displacement along the length of the vector, and we're not worried about direction anymore. All right? And we use the Pythagorean theorem to figure that out. The other part that's sitting here in the graph, so we use the inverse tangent to figure out the angle, right? So go back up. We use the inverse tangent here to figure out, okay, what's the angle that this vector is at, right? What is its angle with respect to x? And I say angle with respect to x because we're taking the inverse tangent of ay over ax, and that gives us the angle with respect to x. If we take the inverse tangent of ax over ay, that'd give us the angle up here with respect to y. All right, that'd give us that one up there. So the inverse tangent ay over x gives us that angle, and we'll talk more about the inverse tangent in a bit. So analytical methods. A plus b is some new vector r, ax plus bx, I hat, ay plus by, j hat, right? Here's our A, here's our B. So our x is ax plus bx, our y is ay plus by. The magnitude of r, we can calculate that, right? Ax plus bx squared plus ay plus by squared. I'll take the square root. And then the angle r makes with the x-axis, right? We can get that angle. And these are our two different ways, our two major different ways to represent a vector. As its components, right? And as its magnitude and an angle. Those are the two ways that we represent vectors all the time, either as its distinct components or as its magnitude and direction through an angle. All right, that's it for part 1 of this lecture.